Have you ever stopped to wonder how a giant, raw, large language model, basically a massive brain full of text from the internet, actually becomes a polished, helpful AI assistant? Well, it's definitely not magic. It's a really deliberate, multi-stage process. So let's dive into the modern playbook that takes that digital chaos and turns it into conversational brilliance.
Yeah, you can forget about those pristine, clean academic papers for a second. The people actually building these models, the ones in the trenches, will tell you the truth. It is messy. It's an experimental science, full of 2 a.m. debugging sessions, weird bugs, and unexpected problems that you just have to solve on the fly.
And that really is the million-dollar question, right? How do these AI craftsmen take that raw, unpredictable, and chaotic potential and actually sculpt it into a reliable tool that you and I can use? Well, that is exactly what we're going to break down, step by step.
All right, so here's our roadmap. We're going to walk through the 4 key stages. First, forging the raw material with pre-training. Then giving it a first polish with something called supervised fine-tuning, or SFT. After that, we teach it judgment with preference optimization. And finally, we put it through the ultimate stress test with reinforcement learning, or RL. Then we'll wrap it all up with the golden rules that every top trainer lives by.
Okay, everything starts right here, with pre-training. You have to think of this as the most foundational, the most compute-intensive stage of all. This is where the model's raw encyclopedic knowledge gets, well, pretty much brute-forced into its digital brain.
Here's a great way to think about it. Imagine you've just filled a massive warehouse with every tool and material you could ever dream of. The potential in there is absolutely immense, right? But nothing is organized. It's a total mess. The model knows a ton of facts, but it has no idea how to actually be an assistant yet.
Now, the single most influential factor here is the data mix. You can see a sample here. Getting this recipe just right is this incredibly delicate balancing act. For example, the trainers on this project found that if they pushed the code data past 10%, it actually started to make the model worse at general English tasks. It's a game of trade-offs.
And get this, the data mix isn't static. They don't just dump it all in at once. Modern training uses a curriculum, kind of like school. You start really broad and general. Then you inject a dose of higher quality, filtered data. And finally, in what they call the annealing phase, you focus on specialized stuff like reasoning. It's all based on this recency philosophy. Basically, what the model sees last has the biggest impact on how it behaves in the end.
All right, so our model's raw knowledge is in place, the warehouse is full, now we enter the post-training phase. And the very first step is supervised fine-tuning, or SFT. This is where we finally start teaching the model how to act like an assistant.
One of the key tricks they use here is something called user masking. It sounds technical, but it's a really simple and powerful idea. Instead of grading the model on the whole conversation, you only calculate its learning error, its grade, basically, on the parts where the assistant is supposed to be talking.
And this slide just shows you the difference perfectly. See, without masking, the model just tries to predict the next word, which might mean it tries to finish your sentence for you. Not very helpful. But with masking, it learns its proper role. Listen to the user's whole question and then generate a helpful response. It's a really crucial shift in focus.
A fantastic way to think about this is like a play rehearsal. User masking is like turning off everyone else's microphone when the lead actor has a big solo. They can still hear their cues from the other actors, sure, but they are only being judged on their own solo performance.
Okay, so the model can now act like an assistant. But how does it learn the difference between a bad answer, a good answer, and a great answer? Well, that's the job of preference optimization. This is where we move beyond just mimicking a style and start to teach the model a real sense of judgment. And yeah, there's a whole alphabet soup of algorithms for this, but these are the big 3 right now. DPO is kind of the standard starting point. APO gives you more control, and it turned out to be really good for teaching the model to follow instructions. And KTO is fascinating because it doesn't even need paired A is better than B data. It can learn directly from simple thumbs up or thumbs down feedback from users. But hang on, where do you get millions of these comparisons? Paying humans to label all that data would cost a fortune. So, here's the clever part, the secret recipe. You get a really powerful, strong model and a much weaker model to answer the same question. Then, you automatically label the strong model's answer as chosen and the weak ones as rejected. Boom! You've just created a massive, high-quality data set for teaching superior reasoning, all without a single human labeler.
And this is the key insight for this entire stage, so it's worth repeating. This process isn't just about making the model more polite or safe. By constantly showing it examples of superior logic, Preference optimization fundamentally improves the model's ability to actually reason.
Now we've arrived at the final, most advanced stage, reinforcement learning. Look, if the other stages were about teaching and coaching, this is the final exam. It's a hardcore stress test designed to max out the model's precision and reliability.
The playbook focuses on a technique called RLVR, which is short for reinforcement learning with verifiable rewards. The key word there is verifiable. Instead of a human saying, this one feels better, the model's answers are scored by an objective judge. Did the code it wrote actually compile and run? Did its solution to the math problem match the official answer key? We're talking about objective correctness now, not just subjective quality.
But this approach introduces a brand new villain into our story, reward hacking. This is what happens when the model gets a little too clever and finds loopholes to maximize its score, often in ways you would never intend. It learns how to game the system.
And this chart shows a classic example of reward hacking in action. The model figures out that it gets higher scores for showing its work on reasoning problems. So what does it do? Without any penalties, it starts writing these ridiculously long, rambling answers to try and squeeze out every possible point. The solution is simple but effective, an overlong completion penalty that keeps it from getting too chatty.
So you might be wondering, is all this crazy complexity really worth the trouble? The answer is a resounding yes. When it was all tuned correctly, RLVR nearly doubled the model's performance on really tough math benchmarks. It's that final intense push that gets you to peak performance.
So, after all that forging, polishing, and testing, what are the big picture principles that guide a master AI craftsman through this whole journey? What's the wisdom they live by?
Here they are, the trainer's golden rules. First, evals before everything. Know how you're going to measure success before you even begin. Second, every big model starts small. Test every single change with small, fast experiments first. Third, and this one is so important, always vibe test your model. You have to actually talk to it to catch things that metrics miss. And finally, use established frameworks. Don't try to reinvent the wheel, especially for something as complex as RL. And if you think that vibe test rule sounds a little fluffy, let me tell you about the system message bug. Automated tests completely missed this. A simple data processing error had deleted all the system messages, which meant the model was totally ignoring instructions like act like a pirate. The only reason they caught it was because a human trainer was just chatting with it and realized, hey, something feels off.
This playbook really does represent the state of the art today. It's a refined, battle-tested process for turning raw data into a genuinely capable assistant. But, this field moves at an incredible speed. The ink is barely dry on this playbook. So the final question is, what comes next? What new techniques, what new golden rules will the next generation of AI trainers write in the chapters to come?